In this video, we're going to go through examples using integrated rate laws. Before that though, I wanted to do a quick summary. So this is a handout that I do have posted on Canvas for you where we compare zero first to second order. So I'm just going to expand this a little bit so it's a little easier for you to see. So concentration, I'm looking at the second row here. So concentration versus time, we get curved lines, right, for first and for second order, right? As time proceeds, our concentration is changing. The only one that we get a straight line for is going to be my zero order reaction. Above that, we have our rate law, right? Rate is equal to K. We did say we could add the concentration raised to the 0 power, but again, that goes to 1. 1 times K is just K. My rate law for a first order reaction, rate is equal to K, the concentration of A raised to the first power, second order, K times the concentration of A squared. For all of them, it's the change in concentration of A over the change in time, right? They all have a negative sign in front of them because A is my reactant in this case, and its concentration is disappearing, right? It's decreasing over time. Going on and looking at our integrated rate laws, right? We said that our first order ones are the ones that have the natural logs in them. It looks weird, but those are my natural logs. The reciprocals were the ones that were in my second order. If I go down to the half-life, right, my first order does have, this is the natural log of 2, and I have the reciprocal of my concentration for my second order. We don't really use zero order a lot, so I wouldn't really worry about knowing this one. I didn't cover it in the previous video. It's here for completion, but don't really worry about that so much. Straight lines, to get a straight line for a first order reaction, we graph the natural log of my concentration versus time. We get a negative slope equal to K. With my second order, we graph 1 over the concentration versus time. We get a positive slope equal to K. Right? For my zero order, it's just straight concentration versus time, the same thing that we had up here. Let me erase some of these as I go. And then this part here that we didn't talk about is just showing that dependence that rate has on our concentration. So what we're showing here in this first column is I'm changing my concentration. So if I go from 1 to 2, if I double it, my rate doesn't change. If I go from 2 to 3, my rate again is not changing. So changing the concentration is not affecting my rate, which is why it's zero order. If I look at this one, this is for first order. Remember, whatever we do with first order to the concentration, the same thing happens to my rate. So if I go from 1 to 2, I'm doubling it. My rate also doubles. If I go from 1 to 3, right, I'm tripling it. My rate is also going to triple. So whatever we do to that concentration, the same thing happens to the rate. And then with second order, right, it's going to be double that. So, or it's that squared, I should say. So if I double it, I go up, my rate goes up 4 times, right? 2 squared is 4. If I triple it, right, this time 3 squared is 9, my rate is going to go up 9 times. So my rate is more sensitive to concentration changes. So just a summary of essentially everything we've done thus far. So let's go through some examples. For this one, I'm going to have sucrose, which is C12H22O11 plus water, and we're hydrolyzing it into 2 glucose molecules. And this is a first order reaction. And we're going to calculate the rate constant if it takes 9.70 hours for the concentration to drop from 0.00375 molar to 0.00252 molar. So because it's first order, we are going to use our first order rate law, integrated rate law, I should say, which is this one. Sorry, that was quick, but I am going to write it down here. And you can use, remember we rewrote it? That's hard to say. Initially, I had it as the concentration of AT over A naught, and then we used our log identities to rewrite it. I like to use both. I think the math is a little bit easier in this case to do it this way. And you could use the other equation, the one that I just kind of did this super quick, right? That's the same one, just using our log identities and rewriting it. I like this form for this problem. So if I'm given in the problem both of my concentrations, I tend to use this version. If you want to use the other version, just for consistency for you, if you find it easier, by all means, we're going to get the same answer. So I'm just going to start plugging numbers into this equation. Please do be careful. AT is my time that it is, or the concentration at time t, and A naught is my initial concentration. It doesn't specifically say in this problem which is initial and which is at time t, but we know that concentration decreases over time, right? This is reactant concentration. So the bigger concentration is going to be my initial one, right? We can't start out with less and make more because this is a reactant, right? Reactant concentration decreases over time. So I'm going to take the natural log of 0.00252 molar, and I'm going to divide it by 0.00375 molar, right? The larger number needs to be my initial concentration when you plug them in. And then mathematically, make sure you do that division before you take the natural log. And then that's going to be equal to negative k, which is what we're solving for, multiplied by my time, which is 9.70 hours. Unit-wise, these molars are going to cancel. Log values aren't going to have units, so those are always going to cancel if you have both of those. And then when I take the natural log and then divide by my time, I'm going to end up with units of negative hours to the -1, or 1 over hours for my rate constant. So I'm just grabbing my calculator, which is the noise you heard. So I'm typing it in. And then I end up that K, didn't really mean to pick every color I have. K is going to come out to 0.0410 hours to the -1, or 1 over hours, however you prefer to write it. Either one is fine. But that is going to be my final answer here. Again, be careful with the math. I'm just going to write this on here. If I have the natural log, I'm just going to use x over y, right? That does not equal, notice this is a does not equal sign, the natural log of x over the natural log of y. That's not true. Be really careful. Don't type that in wrong. It also doesn't equal the natural log of x divided by y, right? That doesn't work neither. So just be really careful when you're doing this. You need to take that fraction first. I don't always write it in parentheses. I assume that you know that you need to do that, so be careful. Right? If we wanted to use our log identities, every time I write natural log, it gets even messier. If I wanted to rewrite this, what it does equal is the natural log of x minus the natural log of y, which is what we did when we rewrote it in slope-intercept form. One other thing before we move on to another example are the units on my rate constant, and we could add that to this table. I'm just seeing if it's here. Because for a first order reaction, your units on your rate constant are always going to be in terms of 1 over time, whatever that time happens to be. So 1 over seconds, 1 over hours in this case. If you're measuring your half-life in terms of years, 1 over year. So we could say our units, I'm just adding one column here, units for K, our rate constant. And again, don't really worry about zero order. So for this one, it's always going to be 1 over some unit of time, which again is the same thing, right, as my time unit raised to the -1 power. I know that's super small, you probably can't read that at all. So my units for K are always going to be 1 over some unit of time. That's another good way to kind of check your work. And it's also a way to tell if something's first order or second order. If you're given an equation and the rate constant is part of the problem and you have to solve for something else and you don't know whether it's first order or second order, look at the units. I will go and add the units for second order after we do a second order example. I do want to do another part to this one. So part 2 to this is we're now going to determine the the time needed to proceed to 80% completion. So we have our rate constant because we just solved for it up here. This time we're going to solve for t. So just writing my equation down again, right? I know that the natural log of this fraction is equal to -kt. This time we're solving for t. K we just have. So then the question is, well, what is that fraction, right? If I want 80% completion, that means 20% of it remains, right? 100% is total reacted, so if 80% is completed, 20% is unreacted. And when we first were talking about first order rate laws, we said that that fraction AT over A naught can tells us the amount that remains at time t. So what I'm going to do is I'm going to plug in 0.2 for that fraction. We can leave that natural log off. So right, if it said determine the time needed to proceed to 20% completion, then I would plug in 0.8. If it said determine the time that it takes for 20% of it to be unreacted, then I would plug in 0.2. Sometimes you have to kind of really think about the wording to know whether you're going to plug in what it's giving you or if you need to subtract that from 100 or 1, right? 1 if you unpercent it. You're not going to plug in the percent. You're going to plug in the fraction, right? This is up a ways, but maybe we can find it. Sorry, it's a few videos back, but it's probably here, first order. Sorry if I'm making you dizzy with the scrolling. Yeah, here we go, right? This is the fraction that remains at time t. So what has been reacted then is going to be the opposite of that. So a couple words, it's the fraction, not the percent, and then remains. Those are important ones. So scrolling back down, that's a ways. Okay, so 80% complete, 20% remains. I want the fraction, so 0.2. So that's what we're actually going to plug in to our equation. So I'm going to take the natural log of 0.20. That's going to be equal to negative of my rate constant that we just calculated. Multiplied by my time. So I'm going to grab my calculator. please, with all of these examples that I'm doing, work through them also. Like if I'm doing it too fast, hit pause after I set it up and plug it into your calculator yourself. You need to be able to do this on your calculator. You need to know where your natural log button is. You need to know what to do with the negatives, right? The log of a number less than 1 is going to be a negative value. So please do the math also. Watching me do all the math isn't going to help you do the math. So again, hit pause if you have to. Get out your calculators. Please, please, please type these in yourself and make sure you're getting the same answer as me. If you're not, make sure you do ask at some point. And I need to stop talking here for a minute so I can type stuff in correctly. And I end up with my time being 39 hours. So it's going to take 39 hours for this reaction to be 80% complete, right? 20% unreacted. I'm going to add one more part to this problem, and that's going to be using half-life. So what is the half-life for this reaction? Using our first order half-life equation, same thing as 0.693 over K, however you want to do it. So I'm going to take 0.693 and I'm going to divide it by my rate constant. Grabbing my calculator. And I get 16.9 hours. So it'll take 16.9 hours to cut in half, another 16.9 hours to cut in half again. If I want to cut it in half another time, it's going to take 16.9 hours, right? For a first order reaction, which this one is, each subsequent half-life is the same amount of time. Ooh, let's do another example. This time I have 2 NOBr and we're forming 2 nitrogen monoxides plus a bromine gas. And this one is going to be second order. And we're going to given our rate constant this time. And it's going to be 0.810 molar to the -1, seconds to the -1. So our units for a second order rate constant are always going to be 1 over concentration time. For first order, remember, it was just 1 over time. If we want to go back up to that table, let me make this a little bit bigger here. For this one, it's going to be 1 over molar, whatever my unit of time is. Could be seconds, could be hours, however we're measuring time, could be years. Again, molar to the -1 times my time unit, whatever that happens to be, to the -1. If we had a third order reaction, which we're not going to really look at, but the units would be molar to the -2 time unit to the -1. So 1 over molar squared seconds, something like that. Okay, back down to our problem. So second order, my rate constant is 0.810 molar to the -1 second to the -1. I wouldn't actually have to tell you this. We could just say the rate constant is equal to this, and we would know that it's second order because of those units. And that is something that you should know. So do know the units for those. So our question, if the initial concentration of NOBR is 7.5 times 10 to the negative third molar. How much is left after 10 minutes? So we do need our equation. Second order were the ones that have the reciprocals again. Again, these are on your equation sheet, but you do need to know which one goes to which order. So initial concentration is given to us in the problem, right? This number is going to be A naught. How much is left? That means AT is what we're solving for. That's my unknown. My time right now is 10 minutes. And then my rate constant K was given to us in the problem. We do have to do something before we can plug these right into my equation. Do you guys see what it is? What's our problem right now? Hopefully you noticed. If not, I will tell you. My rate constant is in terms of seconds, right? My time unit in my rate constant is seconds, but I'm given my time in minutes. So I need to do a unit conversion first. They have to have the same units. Or not the same units, but the time unit needs to be the same. So if my rate constant was molar to the -1, hours to the -1, then I would want my time to be in hours. So we do want the time unit to be the same. If I want to convert my time to seconds, or if I want to convert my rate constant to molar to the -1, minutes to the -1, either way works. I usually convert the time. I think it's easier because the units of my rate constant are in the denominator, right? It's 1/seconds. So I think it's easier to just convert the time, so I'm going to. If I have 10 minutes, how many seconds do I have, right? There's 60 seconds for every 1 minute. So 60 times 10, I'm going to have 600 seconds. Do watch out unit for units. Technically, I should really only have one in my answer, right? Because 10 minutes, because I don't have a decimal point after that 0 is only one significant digit. 600 seconds is one significant digit. So we are okay here. Generally, I would give you 10.0. I would want more sig figs than just one, but I didn't, so this is where we're at. Okay, plugging everything in now, which we can do. Equals this is where if you forgot to convert your time to seconds, hopefully you would catch it, because we do need to be able to cancel these out. And if one is in minutes and the other is per second, we can't cancel them. Okay, so please, again, do the math on your own. I'm going to grab my calculator, but you do need to be able to do this on your own. I'm actually going to do part of the math, and then we can reconvene and do the last step together if you guys want. So I'm going to do everything on the right side. So I ended up with 619. I do, again, my sig figs, unfortunately, I gave you the wrong, so we're just going to go with it. I really only want one sig fig in my answer, so I would round this to 600. I'm going to leave it now, and then we'll round at the end. So my last step, and the reason I'm doing this is people will get this answer and then they'll just stop thinking they're done. You're not, right? At this point, I have 1 over AT is equal to this number. I want to know what AT is equal to. So I do need to take the reciprocal of this number. So I'm going to, oh, and my units right now are molar to the -1, sorry. I'm gonna take 1 over that number. Just a little quick math review to get my final answer. And I get 0.0016. I'm just writing down more digits right now. We do need to round again to 1 sig fig, so 0.002 molar is going to be my answer. If you forgot that last step, then hopefully you're thinking about this and it makes no sense, right? This is the concentration of my reactant. If I'm starting out with 7.5 times 10 to the -3rd, right, 0.0073, there's no way that I can have 619 molar, right? It's decreasing, not increasing. So your answer needs to be smaller than what you started out with, right? I had 7.5 times 10 to the -3rd. I now have 2 times 10 to the -3rd if you were to put it into scientific notation. So do think about your answers. It's a really great way to catch your mistakes, right? If you're thinking about what you're doing. So do pay attention to those sort of things. We're going to calculate our half-life also. For this one, though, we do have to be specific because the half-lives change. So for our first order, I could just say, what is my half-life? Here, my first half-life is different than my second half-life, which is different than my third half-life, right? With second-order reactions, each subsequent half-life is twice as long. So we do need to be specific. So I'm going to say, what is my first half-life? If I wanted the second, I could just solve for the first and then double that amount of time. So using our half-life equation, I have that my half-life is equal to 1 over my rate constant multiplied by my initial concentration. So plugging those numbers in, my half-life was 0.810 molar to the -1, seconds to the -1. Didn't really leave myself enough room here. And my initial concentration, is 7.5 times 10 to the -3rd molar. Units, these are going to cancel. And then 1 over seconds is just going to be seconds for my units. So grabbing my calculator here. Again, please, please, please be typing these in also. And it comes out, when I type it into my calculator, 164.6. I do want to round it to 2 significant digits. 7.5 is 2 sig figs. So I'm going to have 160 seconds for my answer. So I want to do one more example before I set you loose to do your own practice. So this one, if each half-life for a given reaction is 18.2 minutes, what will the concentration be after 450 seconds if the initial concentration, being lazy here, was 2.4 molar. So I want you to try this one on your own first. So please hit pause, work this one out, and then we'll check the work. Do note that it doesn't tell you in this if it's first order or second order. You do have to determine that for yourself. And you can get that from the wording, right? If each half-life is 18.2 minutes, that tells us if it's first order or second order. So again, please hit pause, give this a shot on your own, and then when you're ready to compare your answers, hit play again. All right, hopefully you guys gave it a shot. So each half-life, right, it's first order. Remember that the half-lives are constant for a first order reaction. So if each half-life has the same value, I know it's a first order reaction. So first order, right? The half-lives are constant, right? Each one is the same for first order reactions. So that's how we knew what this is. So we're not given our other problem right now that we've determined this, kind of what's our problem, is we don't have K. We do need K, right? I know that the natural log of AT over A naught is equal to negative KT. If you wanted to use the other version, which is fine, I may do that in this one, the natural log of AT is equal to negative KT plus the natural log of A naught. The reason I would probably use the second one instead of the first one is because I'm given one of the concentrations in the problem, and I think it's easier this way. But either one, again, will work. I tend to mix it up. We can do it. You could try it both ways to prove to yourself that you're going to get the same answer. I know T is 450 seconds, right? I know that A naught is 2.4 molar. I know that AT is my unknown. And then we're given our half-life also of 18.2 minutes. My problem is I don't have K, right? Right now, looking at this equation, I have two unknowns, right? What I'm solving for, and my rate constant, because it wasn't given to us as part of the problem. However, we can use our half-life equation to solve for K. Once I have K, we can then plug that into our equation. So we're going to use our half-life equation, right? Natural log of 2 or 0.693 over K to solve for K. So I have 18.2 minutes is equal to 0.693 divided by my rate constant. So solving for my rate constant, I get 0.0381 minutes to the negative 1. So that is no longer a question mark, right? I now, though, do need to look at my units on time. My units on time up here are in terms of seconds. My rate constant is per minute. We do need to make sure that those have the same unit for time. So I'm going to divide 450 by 60 to get 7.5 minutes. So our unit conversion. We now should be able to just plug everything in. And maybe I'll do this first one. I think the math, I want to go through the more difficult math. I mean, it's either way, it's really not that tricky. It's just that we do need to remember that it's the natural log of that fraction. So plugging everything in, I have the natural log of my unknown over 2.4 molar. And again, that's in parentheses, negative 0.0381 minutes to the negative 1 multiplied by 7.5 minutes. So unit-wise, my minutes are going to cancel here. And I'm going to just do the math on the right first. So I'm taking my 0.0381, I'm typing into my calculator right now incorrectly, so now I'm retyping it into my calculator. And I got a negative 0.2, I guess I just want two significant digits, 29. So our deal right now is this is in parentheses, right? So I need to unnatural log it first. I need to take the anti-natural log. So remembering our algebra, or just math in general, I guess, to do that, what we're going to do is we're going to take e and we're going to raise it to that 0.29, right? If it was log base 10, we would take 10 and raise it to that. Here we're going to use e. On my calculator, it's actually the second function, natural log key. So please, if you haven't used this before and you're not sure where it is, you're going to see a button that probably says e raised to the x power. It could look different. I have a Texas Instruments calculator. If you have a Casio, it may look a little different. But my natural log button looks like this. It's supposed to be an N, not an M. And then right above it on my calculator, I have that e to the x. So I'm going to use the second function, natural log, to solve for this. So let's do that. And I got 0.75 when I do that. I can now multiply that number by 2.4, and we're finally at our answer. And I got 1.8 molar.